Welcome back to Carneades.org. Today we're going to be continuing with 6 months of set theory and higher order logic. In this video we're going to be looking at A. The set of A equals the set of A and A. A proof of that claim. So, early in the series we stated that sets can only have a particular element once. That a set is defined as having the same member twice is just identical to a set with that member only once. If we have listed in our brackets the same object, set, class, what have you, listed more than once, that is redundant. It means that the set only has one of that object. Set, class, what have you. But, so we stated that a ways earlier, and we said this is just how sets work. But now that we have axioms and definitions, we can actually prove this claim. Specifically, now that we have our definition of curly brackets, it's really formal and specific. So, the claim we're trying to prove, in other words, is that for all classes A, B, and C, if B is defined as the class of A, and C is defined as A, then B is identical to C. Or in other words, for all A, all B, and all C, if B equals A, and C just equals A, then B equals C. I encourage you, try proving this on your own, or if you want to see me do it, keep watching, and let's get started. So, you can tell how long these proofs are going to be just by the size of the font. All right, for all A, and all B, and all C, B equals the set of A, and C equals the set of A, implies that B equals C. So we're going to do this with an assumed indirect proof. So we're going to deny our big long statement of universals, show that that leads to a contradiction, and then we're going to conclude that it is true, because to deny it leads to a contradiction. So let's see how we can do that. Well, we use change of quantifier 3 times, actually. We're not going to do it once each time because it's a long enough proof as it is. To get there exists an A, there exists a B, there exists a C, and then the negation is now inside those quantifiers. Then we'll do existential instantiation. We're actually doing it 3 times. A is instantiated to D, B is instantiated to E, and C is instantiated to F. Right now what I'm trying to do is we're trying to do those in the same order. We're going to get a lot of variables in this proof. So to keep sense of them, we're trying to keep them in order. So, for example, A is being instantiated to D because D is the first one, B to E because E is the second one, so is B, C to F because the third one. Hopefully that makes sense. Then we're going to do, whenever you're denying an implication, you want to use implication and then De Morgan's law and double negation to get a conjunction, and then simplify out the parts of that conjunction that you need. So we have, basically, it's not the case that E equals F, but it's also the case that F is the set of D and E is the set of D and D. So we simplify the 2 parts of the conjunction out, and look, we have another conjunction, so we can simplify that as well. Now, we're going to use an instantiation of our curly bracket definition. Now, I wanted to, when we're using this in this proof, I want to really state it very explicitly here because it's a definition schema instead of a normal definition like we're used to. So this hopefully will help give you a sense of how you can use these schemas. We've already seen one schema with the axiom schema of separation. If you didn't really get how to use that, hopefully this is another chance for you to get into an understanding of how to use schemas in proofs. So we have for all G, all H, and all I, once again noting that we're trying to go G, H, I, just the next 3 letters. We'll see what we actually end up instantiating them as, because we haven't instantiated them yet. These are just using the next letters in the alphabet. So this is saying that for all G and all H, H equals the set of G, equals to, by definition, for all I as a member of H is materially equivalent to I equals G. So to give you a sense of what's happening getting from the curly def to this, our long list of A1, A2, A3, all up to AN is being just replaced by for all G. Because we only have one member we have to worry about because we're going to work with our F equals D first, or F equals the set of D rather. And then we're basically saying that by definition is just to say that for any object, set, class, what have you, I if I is a member of H, that's materially equivalent to I being a member of G, or I being equal to G, rather. So we're going to universally instantiate this. We get F in the place of H and D in the place of G, and we're going to leave I alone because we can't really universally instantiate that until it's outside, until it's on the outside of our statement. So, but we can get it outside our statement pretty quickly because we have already F equals the set of D up in premise 8. So using the law of identity along with premise 10 that says that F equals the set of D is just equal to, by definition, for all I, blah, 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 blah. We can use identity to get that out. Now, we're going to use our axiom of extensionality. Remember, the axiom of extensionality tells us that if two sets have all the same members, then those sets are equal. It should make sense that we're using the axiom of extensionality in this proof. If you were doing kind of an informal proof where you were just stating the axioms that show what's going on here, you would probably need to say the axiom of extensionality, because really what the center of this is saying is that B and C just have all the same members. The only member they have is A. So we'll use the axiom of extensionality, and we're universally instantiating E and F in for our A and B that go on there. Okay, now we earlier got, it's not the case that E equals F, because remember we're doing an assumed indirect proof, so we're denying this conclusion, so that means we can deny the first half of it using modus tollens. And we'll use a change of quantifier to get the negation inside the quantifier, and then existentially instantiate J to K. And we're going to use K for a lot of the rest of the proof. So note what we have here is it's not the case that K as a member of E is materially equivalent to K as a member of F, which it should be if E and F are the same set, which is what we're trying to prove. So now we're going to use our curly definition again, but this is a little more complicated because we have two things. So L and M are both standing in for parts of our list of A's. So we had A1, A2, A3, and so on. Each of those is being instantiated as one of the long list of A's. And AN, for all N is being instantiated into that kind of B, that name of the set, not the members of the set. So in this case, the class N is equal to the class of L and M, equals to, by definition, for all P. P as a member of N is materially equivalent to either P is L or P is M. Hopefully that all makes sense of where we're instantiating each of those. Take a look at the curly definition again. That's in what is pairing, if you're curious for more on that. Now we're going to universally instantiate three different things. L, M, and N are being universally instantiated here from premise 16. And apparently we switched variables on the P. Don't worry, that didn't need to happen, and I could have just started with Q. That variable doesn't matter that much. I'm not sure why I switched variables there, but clearly I just wanted to be using a Q instead of a P. All right, so E equals the set of D and D, which we see earlier. That's what we're trying to use in there, so that's why we're instantiating that there. And then we're just basically instantiating both L and M as D here, because that's what our statement says. So we can get from premise 7 earlier simplification that E is equal to the set of D and D. And so we can conclude that for all Q, Q as a member of E is materially equivalent to Q equals D or Q equals D. Once again, I don't know why I switched from P to Q there. It should just be the same variable, but we're going to stick with Q. So now we have, from premise 19, universal instantiations, we're instantiating our Q to a K. Maybe I wanted them to sound similar. Q, K, who knows? K is a member of E is materially equivalent to either K equals D or K equals D. We can use tautology to simplify that further, remembering that tautology is a rule of replacement, so we can do it inside parentheses, and simplify K equals D or K equals D down to just K equals D. And then we can universally instantiate premise 11 all the way back there when we had for all I to K, because we're universally instantiating, we're allowed to use a variable that we've already listed. So we now have k is a member of E is materially equivalent to k equals d, and k is a member of F is materially equivalent to k equals d. Now, if we had an easier way of dealing with equivalences, the rules that we use take a long time with that, hopefully you would see that this should mean that k as a member of E is materially equivalent to k as a member of F, because those are just biconditionals, those triple bars. And so in some ways they work similar to conditionals. And so we should right here have very clearly the building blocks of something that is the opposite of premise 15. That will contradict premise 15. So everything we do from this point forward is just trying to get to that basic intuitive idea that if k as a member of E is materially equivalent to k equals d, and k as a member of F is materially equivalent to k equals d, that means that k as a member of E is materially equivalent to k as a member of F. All right? Hopefully that made sense. Well, we'll do it explicitly if it didn't. So premise 21 equivalence and premise 22 equivalence, we're going to do this kind of simultaneous proof that we sometimes do. Those are just 21 and 22. We're expanding our biconditional. And then we're going to simplify 23 twice into the two halves of that conditional. And we'll do the same thing with 24. So we now have 4 conditional statements of implication. And we're going to recombine those into a new equivalence. First, to do that, we'll use a rule that we rarely use, which is hypothetical syllogism. We have 2 implications, and we need those implications to run together. So k as a member of F implies k as a member of E from 26 and 27. Basically, think of it as kind of lining up where we have that implies k equals d and smushing them together. And we'll do the same thing again with 25 and 28 and another hypothetical syllogism. These are 2 conditional statements. We can combine those 2 conditional statements with a conjunction and use equivalence to turn that into our equivalence. Hopefully that looks familiar because it's the opposite of premise 15 back there. We can join them. We have a contradiction. Therefore, we can conclude 1 through 33 indirect proof for all A, all B, and all C. If B is the class of A, and C is the class of A, that implies that B equals C. Whew! If you thought that was long, just wait. Next up, we're going to show that if the set of A equals the set of B, if and only if A equals B. These are great opportunities for you to test your own advanced logic abilities, so I would highly encourage you to try on your own to prove these statements. If you want to come with me into the first part of the video so you see the exact statement, because this isn't exactly what we're proving a statement with a bunch of universal quantifiers in front of it. So if you want to see exactly what we're proving and then pause the video, that's a great idea too, but either way, I really encourage you, give these a try on your own. You'll learn a lot more by engaging with it. Whew! Watch this video and more here at Carneades.org, and stay skeptical, everybody.